And then what I forgot to say is that these integrals are, that's easy to see, these integrals are bounded by the integral of g. Because of this assumption. So the integral of f plus is finite, and the integral of f minus is also finite. And this is equivalent to saying that f is integrable, right? So these inequalities imply that f is in L1. And then, I mean, to prove this limit statement, well, integral fm d mu by definition of the integral is integral fn plus d mu minus integral fn minus d mu. And now we know that this converges, we know that this converges, both terms are finite, so the difference converges to integral f plus d mu minus integral f minus d mu, which is by definition the same as integral f d mu. And that's the proof. Any questions? Okay, so this is the dominated convergence theorem, and then to kind of illustrate that this is useful, we can immediately show one corollary. The statement is let x sigma mu be a measure space. F an integrable function. And then say we have a sequence of measurable sets. En. Which are disjoint. And then we want to say something about their union, so denote by E their union. Then the following is true: integral over E f d mu is equal to the sum n equals 1 to infinity integral En f d mu. I think we had a similar statement for non-negative functions, and there we used the monotone convergence theorem to prove it. But here, f can be any integral function. Can be positive, can be negative. And this we can prove with a dominated convergence theorem as follows. I mean, okay, we have the sequence of sets En, so to apply the dominated convergence theorem, we need the sequence of functions Fn, so define Fn to be the characteristic function of En times F. Actually not the characteristic function of En, but the characteristic function of a finite union of Ens. So union k equals 1 to n ek times F. And then this is the same as the sum k equals 1 to n chi ek times F, right? Because the characteristic function of a union of disjoint sets is just the sum of the characteristic functions of the individual sets. Okay, so this is a nice sequence of functions. Then clearly Fn converges to F pointwise. And Fn absolute value is bounded by the absolute value of F. Almost everywhere, I mean, it's true everywhere. So this boundedness assumption of the dominated convergence theorem is satisfied with G equal to mod F. And this convergence assumption is satisfied, so we can apply the dominated convergence theorem. Which implies that the Fn converges to chi e times F, not F. Because E doesn't have to be the entire set X, it's just some set. So the limit is chi e F. But everything else is still true. And then by the dominated convergence theorem, the integral of chi e F d mu is the same as the limit n to infinity integral Fn d mu. But I mean, the left-hand side is by definition equal to the integral of E F d mu, and the right-hand side is limit n to infinity, and then Fn was this sum, integral sum k equals 1 to n chi e k f d mu. And now this is linear, so this sum, we can swap the sum and the integral. And then the limit just gives a sum from k equals 1 to infinity. And the integral of chi ek f is the same as the integral over ek of f. So this is the same as sum k equals 1 to infinity integral ek f d mu, which is exactly what we wanted to prove. Okay, so this is one example of how one can apply this dominated convergence theorem to get new results. Are there any questions about this? proof. Okay, if that's not the case, we come to the last part of this section, which is concerned with the connection between the Lebesgue integral and the Riemann integral. So, I mean, we've derived many nice properties of the Lebesgue integral now. We know that it's linear, we know its behavior under taking limits and so on. We can compute the Lebesgue integral in some simple cases. And these are all properties that we would expect to be true for an integral. But we don't actually know whether, in the simplest case, in one dimension on the real numbers, whether it gives the same as the Riemann integral, which should be true, right? We want the Lebesgue integral to be a generalization of the Riemann integral, to be something, to be useful. And this is precisely what the next theorem says. So theorem 4.43. So this was corollary 4.40, and then in between there were some remarks which I'm omitting here, so if you're interested, look at the lecture notes. This is theorem 4.43. Let f be a function on an interval on the real line, which goes to the real numbers. Assume that f is bounded. And Riemann integrable. And the statement is that then f is Lebesgue integrable. So to make this precise, this means that f is an element of L1 of the measure space interval AB, comma, sigma L, Lebesgue measurable sets, and the Lebesgue measure in one dimension. So f is Lebesgue measurable on AB, and the Riemann and Lebesgue integral are the same. So this is really a thing that has to be true if we want, if the Lebesgue integral is reasonable, then this theorem should be true. Okay, and the proof is actually a nice illustration of how the Lebesgue integral is a generalization of the Riemann integral. So just a brief recap. I hope you vaguely remember how the Riemann integral was defined. For the Riemann integral, you take this interval and divide it into small pieces, and then on each piece you bound f from above and you bound f from below by a constant, and then you take the sum of all these upper bounds times the length of the small interval and the sum of all the lower bounds, and then f is Riemann integrable if the difference between these upper and lower sums goes to 0, and then the limit of these upper sums is the Riemann integral, which is equal to the limit of these lower sums. So essentially there are two step functions involved. One lies above f and the other lies below f. And the step size becomes more and more narrow. And if f is such that that thing converges, then it's Riemann integrable. And well, essentially these step functions that are above and below f, they're the same as simple functions. They're not the same, but they're a special case of simple functions, right? And this is how the proof goes. So we construct these upper and lower sums, and then we construct, and then these step functions are simple functions, and we use these simple functions to conclude something about the Lebesgue integral of f, and eventually show that the two integrals are the same. Okay, so let's begin the proof. Before we begin, without loss of generality, we can assume that f is non-negative, because if it isn't, we assume that f is bounded, right? So if it's not non-negative, we can just shift it up by adding a constant, and then it is non-negative. And then if for f plus c, the Lebesgue and Riemann integral are the same, then they're also the same for f. Because the integral of a constant in the Lebesgue and in the Riemann case is the same. That we know already, right? It's just the length of the interval times the constant. So we can assume that f is non-negative. And then we start with this procedure of constructing Riemann integrals. So we take this interval and we divide it. So let delta n be an equal partition of this interval AB, into 2 to the n pieces which we call J1 up to J2 to the n. So the index is the number of the integral, the interval, and they should be such that J1 is closed, and all the others are closed at the right-hand edge. So if this is the interval AB, then okay, it's divided into 2 to the n pieces, and then the first interval is on the left hand side here, is closed, and then the others are open on the left hand side and closed on the right hand side, and so on. So this is the sequence of intervals J and K. Okay, and next define lowercase mk to be the infimum of f on the interval jk closed, and uppercase mk to be the supremum of f on jk. And then we define the lower and upper sums of f. So L for lower, L of f comma delta n to be the sum k equals 1 up to 2 to the n, and k lowercase 2 to the minus n. So this is the lower sum, right? This nk is a lower bound for f on the interval jk, and this 2 to the minus n is the length of the interval jk. And then we do the same with the capital M's. So u for upper of f comma delta n is the sum k equals 1 to 2 to the n, uppercase mk 2 to the minus n. So these are these Riemann sums. Okay, so up to now everything was just definitions. We just set the scene for what's coming. And now we're going to compare the Riemann integral and the Lebesgue integral of f. And that's going to be slightly annoying because we need two different notations for the two different types of integrals. So what I'm going to do is I'm going to write r in brackets and then integral a to b f dx for the Riemann integral. And I'll write L in brackets, integral a to b f dx for the Lebesgue integral of f. So whenever there's an integral, I will either write this or this to specify whether it's the Riemann or the Lebesgue integral. Okay, so we have these upper and lower sums. And we assume that f is Riemann integrable. So we know something about these upper and lower sums. So because f is Riemann integrable, we know that the upper sum f comma delta n minus the lower sum of f comma delta n goes to 0 as n goes to infinity. So we get that for free from our assumptions. And then we can do the following. We can define two simple functions. Phi n to be the sum k equals 1 to the n mk times the characteristic function of jk, and phi n to be sum k equals 1 to 2 to the n uppercase mk times characteristic function of jk. So these are clearly simple functions, right? These jk are measurable sets because they're just intervals. And then this uppercase m and lowercase m, they are non-negative numbers, and the sum is finite. So these are simple functions. And moreover, by the definition of this uppercase m and lowercase m, right, int f and sub f, we know that phi n is less than or equal to f, and f is less than or equal to psi n. And in addition, we know that phi n is an increasing sequence of functions, and psi n is a decreasing sequence of functions. These two might not be completely obvious, but if you look at the definition, it becomes clear. So let's look at phi n. Phi n was defined to be this. So it's the infimum of f. So on each interval jk, it's equal to the infimum of f. Now if we increase n, because we have 2 to the n intervals, if we increase n by 1, it just means that every interval gets divided in the center. So the new mk will just be